We are going to use initial rate of reaction to determine the rate law for a given reaction. So we know that a rate law can be written as a product of the concentrations multiplied by a rate constant K. So for this reaction, our rate will equal K, our rate constant, times the concentration of X raised to some exponent, times the concentration of Y raised to some exponents. Now these exponents are not necessarily related to the coefficients. So we have to determine the value of X and Y using experimental data. So we're going to look at now our data which has concentrations of X and concentrations of Y and the rate of appearance of Z. And we're going to look at how changing the concentration changes the rate. So the first thing we're going to do is solve for how X affects the rate. And so we want to pick two trials in which the value of X changes. And we see that from trial 1 to trial 2, our concentration of X has doubled. In the same trials, we see that our concentration of Y has not changed. And we want to make sure that we pick two trials where the concentration of one substance has changed and the concentration of the other substance has not. This means that Y, in this case, is our controlled variable. We're making sure that the concentration of Y does not affect how the rate changes when we alter the concentration of X. So now we see that we've doubled the concentration of X. We're now going to look at how the rate changed when we did that. So our rate went from 0.2 to 0.4, which is an increase of 2 times. So we see that the increase in the concentration of X and the corresponding increase in the rate is the same magnitude. That implies to us that the exponent X must equal 1. Now, if this is not as easy to intuit, we can mathematically show this. And to do that, we're going to take a ratio of our rates and our rate laws. So we're going to start by the rate law for trial 2 is equal to our rate constant times the concentration of X for trial 2 and the concentration of Y for trial 2. Then we divide that by the rate law for trial 1. We know that the concentration of Y for trials 1 and 2 is the same, so we can cancel out this entire term. We also know that our rate constant won't change from one trial to the next, assuming we keep the temperature the same. So now we're left with the ratio of our rates is equal to a ratio of our concentrations. So our rates ratio will be 0.04, and I won't include units here just for simplicity, over 0.02, and that's going to equal, now we can put our concentrations into one fraction, so 0.20 over 0.10, and we can raise both of these numbers to one exponent. So simplifying, that gives us 2 equals 2 to the x, and using logarithm rules, we can then determine that x equals 1. Now, most times you're going to just be able to look at the magnitude of the change and deduce what the exponent should be. If you're struggling, this method will give you an answer. If you don't get a whole number here, you're going to round to the nearest whole number. So now that we've solved for the exponent for x, we're going to do the same thing for y. And this time we want to pick two trials where the concentration of y changes, but the concentration of x doesn't. So we see that the concentration of y changes from trial 1 to 3 and from trial 2 to 3. However, the concentration of x is only constant for trials 1 to 3. So we want to pick trials 1 to 3 to determine the exponent for our concentration of y. So from trials 1 to 3, we see that our concentration of y has doubled. It's increased by a factor of 2. For the same trials, we see that our rate has increased by a factor of 4. So every time we double our concentration, our rate increases by a factor of 4, which implies that the exponent on y is going to be 2. So we can rewrite our rate law as the rate is equal to k, our rate constant, times x times y squared. And the last thing we want to do is to solve for the value of k for our rate constant. So we can pick any trial, substitute in the numbers from that trial for the rate and our concentrations, and solve for k. So I'm going to pick trial 1. I'm going to rearrange this equation first. So k is going to equal the rate over the concentration of x times the concentration of y squared. And now we can plug in our values. The units here are very important. So we're going to plug in 0.020, and the units for rate are moles per liter seconds. And so our concentration, we have 0.10 moles per liter and 0.10 moles per liter squared. If we look at our units, we will see that moles cancel here and liters cancel here. So the units of our rate should be liters squared, and that comes from the denominator here, liters squared, over moles squared times seconds. So liters squared here, moles squared here, and we have the seconds remaining from our rate. And we get a rate constant of 20 liters squared per mole squared per second. The units of your rate constant will depend on the exponents in your rate law, so may be different for different reactions you study. So we can rewrite our rate law now with our rate constant as the rate equals 20 liters squared per mole squared seconds times the concentration of x times the concentration of y squared. And the value of 20 that we have here is only true at the temperature we studied. So the rest of the rate law will be the same, but that value for k changes with temperature.